For a human to work in space, he or she must have a spacesuit. It protects the astronaut from the vacuum beyond the atmosphere, supplying oxygen as well as insulation from the extremes of heat and cold. The spacesuit has to have means of communication with the outside world, and it must enable freedom of movement. The modern spacesuit is the result of a long and complex evolution. Long before humans had traveled to space, aviators wanted to fly at heights that could not support life. In 1932, Auguste Piccard flew above 16,000 meters in a helium-filled balloon. To stay alive, Piccard ascended in an aluminium pressure vessel fed with compressed air. Spanish aviator Emilio Herreras came up with a different solution. His stratospheric suit never flew. It was an idea ahead of its time. In the United States, aviator Wiley Post had supercharged his plane, the Winnie Mae. It could fly at 15,000 meters, where the jet streams blow. Post knew he could save fuel and fly faster at that height. So with the help of tire maker B.F. Goodrich, he devised the first serviceable pressure suit. At this time, even military aircraft were flying at much lower altitudes, where the use of a simple oxygen mask was enough to ensure pilot efficiency. However, as jet power was introduced, operational ceilings lifted. At high altitudes, low ambient air pressure meant the oxygen mask would lift off the face when oxygen was fed to the pilot at pressures high enough to sustain life. When bombers like the B-36 began long-duration missions at high altitudes, they adopted pressurized crew compartments. Yet the pressure suit, with a fully enclosed helmet, was necessary as sudden cabin depressurization could be lethal. In the 1950s, partial pressure suits became common. They had inflatable capstans that stopped blood draining to the legs under heavy G-forces, avoiding blackouts. Air crews hated them, but figures showed they functioned more effectively when wearing them. In 1955, a unique American spy plane made its first flight. The following year, the U-2 began reconnaissance missions over the Soviet Union. Flying at 21,000 meters, it was beyond the range of Soviet radar, and neither jet fighters nor missiles could reach it. Pilots flying the U-2 wore a new partial pressure suit, the MC-3. Rather than save a pilot's life in case of sudden depressurization, this suit was designed to be under pressure throughout the mission. Without it, the pilot's blood would boil. As missile technology developed, it appeared that human beings would be dispensed with as a weak link, not able to cope with conditions imposed by the technology. But the US Air Force had different ideas. They felt that a pilot could make better decisions than a guidance system, and they began a research program using hypersonic aircraft to learn about the problems associated with ultra-high speed, ultra-high altitude operations. The culmination of this program was represented by the X-15, a rocket-powered aircraft that could fly to the edge of the atmosphere. Because of its limited fuel load, the X-15 was launched from beneath a B-52 bomber at an altitude of 15,000 meters. The cabin of the X-15 was pressurized with nitrogen to reduce the risk of fire. For the pilot, a new full-pressure flight suit, known as the XMC-2, was developed. It too was pressurized with nitrogen. A neck dam excluded the nitrogen from the helmet, which was fed with oxygen for life support. This suit was the predecessor of NASA's most important spacesuits. The X-15 set the speed record for a powered aircraft at well above 7,000 kilometers per hour, and the altitude record at just over 107,000 meters. The first real spacesuit was worn by Russian cosmonaut Yuri Gagarin. In 1961, aboard Vostok 1, he became the first man to orbit the Earth. His suit, the SK-1, was to protect against capsule depressurization and to sustain him during ejection from his craft. The Vostok cosmonauts had to parachute to the ground because their capsules landed too heavily. Since 1959, the newly formed US space agency, NASA, had been working towards launching an American into space. 7 test pilots had been selected as the Mercury program's first group of astronauts. The first attempt would be a short hop. As the only booster available at the time, the Redstone lacked the power to reach orbit. An important part of the preparation involved the development of a spacesuit. As a starting point, NASA looked at the XMC-2 used for X-15 flights and the Navy's aviation pressure suit, the Mark IV. Both were full pressure suits. NASA decided that the Mark IV suit, worn here by Alan Shepard, was lighter and could be more easily modified for spaceflight. The boot leather and the suit's grey outer covering would be replaced by aluminized nylon for greater thermal control, and the helmet's rubber diaphragm surrounding the face was eliminated, with oxygen now entering via a hose at the waist to help cool the suit. For all 6 manned Mercury missions, the Mark IV suit performed well, but the demands placed upon it were modest. Like most pressure suits at the time, it served as a backup in the event of cabin pressure failure. Because this never happened on the Mercury flights, this suit was only ever pressurized at launch. In the early 1960s, the Soviet Union's space program was achieving an impressive list of firsts. For the United States, this was a source of national embarrassment. In 1961, the new president, John Kennedy, had boldly proclaimed that America should land a man on the moon before the end of the decade, and NASA was flooded with funds. This was the beginning of the space race.
I don't think we ought to waste any money, but I think we ought to do the job. And this will be done in the decade of the 60s.
The Mercury program was terminated early, in favor of a more complex series of missions with the aim of solving problems associated with sending a man to the moon. The Gemini program made use of a new 2-man capsule boosted to orbit atop a modified nuclear missile. Gemini required a new suit with new capabilities. NASA now understood future missions would have to last much longer. Suits would have to be more comfortable, and astronauts would have to leave their spacecraft in the vacuum of space. Gemini controllers were planning the first spacewalk. In the less open Soviet Union, they were also preparing for a spacewalk. Cosmonaut Alexei Leonov was practicing with an inflatable canvas airlock in temporary weightlessness in an aircraft in a parabolic flight path. He was wearing a new spacesuit, the Berkut, designed to function outside his Voskhod spacecraft. The airlock was needed because the new Voskhod still did not have solid-state electronics. Its thermionic valves needed air cooling so the capsule could not be evacuated. In March 1965, Alexei Leonov left the airlock on Voskhod 2 to float freely in space. It was another first for the Soviet Union. Soon, his Berkut spacesuit began ballooning to such an extent that Leonov could not reach his camera's shutter release, positioned on his leg. It was not until after the fall of the Soviet Union that the full story became known. The Berkut spacesuit had expanded so much that Leonov could not get back inside. Only by venting his spacesuit could the cosmonaut regain entry to the Voskhod capsule. Back at NASA, they heard that Leonov's spacewalk had been a resounding success, but they felt the Gemini program was catching up. In June 1965, astronauts Jim McDivitt and Ed White were preparing for the world's second spacewalk. Gemini 4's launch went smoothly, and on the third orbit, Ed White left the capsule. Although they didn't know it, the greater sophistication of the Gemini craft made this spacewalk much simpler than Alexei Leonov's just 2 months earlier.
Okay, I'm out.
It was easy to depressurize the entire capsule, so no airlock was needed, and Ed White's spacesuit was fed through an umbilical connected to the spacecraft. Leonov carried his own oxygen in a backpack that made re-entry to the Voskhod capsule that much harder. Within the structure of the Gemini suit was a mesh that prevented the ballooning problem experienced during the Russian spacewalk.
I'm just like $1 million.
The first American spacewalk went so well that NASA assumed working in space presented few obstacles. White's joyride in space gave no indication of the difficulties that lay ahead. The Gemini program had a number of goals, and in December 1965, Gemini 6A and Gemini 7 achieved 2 of them: rendezvous and long-duration flight. The crew of Gemini 7 remained in orbit for 14 days. Mission planners knew that staying in a spacesuit for 2 weeks would be a challenge, so a new version of the G3C spacesuit, called the G5C, was worn by the Gemini 7 astronauts. It replaced the pressure helmet with a zippered hood, and Frank Borman and Jim Lovell became the first people to remove their spacesuits in flight. New technologies were being pioneered in the Gemini spacecraft, and problems with the new systems often meant Gemini flights were only partially successful. The capsule had to be capable of far more complex maneuvers than its predecessor, and longer duration missions required fuel cell technology for electric power. In March 1966, Gemini 8 had successfully rendezvoused and then docked with a target vehicle. But a thruster problem sent the linked craft into a spin. The mission was immediately terminated. The scheduled spacewalk did not take place, and the craft landed in the Pacific, half a world away from the planned landing area. 3 months later, Gemini 9 could not dock because its target vehicle's fairing had not been jettisoned. The scheduled spacewalk went disastrously wrong. When Gene Cernan inflated his suit, it did not want to bend. Exhaustion and a fogging space helmet saw Cernan called back inside. He was overheating. Training for a spacewalk was limited to brief periods of weightlessness in an aircraft, or being suspended in a special jig that moved via an air suspension system across a smooth floor. Neither provided anything like the real thing. Engineers had realized that the current generation of spacesuit worked well sitting in a spacecraft, but when doing strenuous work, its air cooling system was inadequate. New designs were already in train. The next 2 Gemini flights both failed to demonstrate that an astronaut in a spacesuit could do meaningful work in space. Before the final Gemini flight, a new training simulation was tried. A mock-up of the Gemini craft docked to an Agena target vehicle was built in the McDonough School indoor pool. An approximation of the true weightless environment, it allowed astronaut Buzz Aldrin to train for extended periods. Handholds were fitted to the outside of the spacecraft, and the extravehicular work assignments on Gemini 12 were a complete success. It gave NASA planners the confidence to move to the Apollo program and the final stages in America's progress to its moon landing. By 1966, it was apparent that Apollo was well behind schedule. The first manned flight of the program had been delayed by almost a year because of developmental problems with the Apollo spacecraft. NASA was rushing to meet the 1969 moon landing deadline set by President Kennedy, and privately some in the astronaut corps felt that the hurry was not good for the development of a new capsule. NASA had flagged changes to later models of the spacecraft, but the early Block 1 version would still carry a crew in the first manned mission to test systems in Earth orbit. A new spacesuit was being developed for use on the later moon missions, but it would not be ready for Apollo 1, whose astronauts, Gus Grissom, Ed White, and Roger Chaffee, would wear a slightly different version of the Gemini GC4 suit. All American spacecraft had been pressurized with pure oxygen. This had weight-saving benefits, and by exclusion of nitrogen found in natural air, the danger of bubbles forming in the bloodstream during rapid decompression was eliminated. Though the pure oxygen environment presented a fire danger, nobody had thought to check the real risks. In January 1967, less than a month before the scheduled launch date, the Apollo 1 crew were in their capsule under simulated launch conditions, with the craft being tested under its own power. A spark triggered a fire, and in seconds the crew were dead. The inquiry into the fire found the astronauts had died of asphyxiation from carbon monoxide. Both the spacesuits and the cabin made extensive use of combustible materials. For the program to continue, everything would have to be redesigned. Research into the problems associated with a spacesuit that could be used on the moon had been going on since 1962. The new suit had to be rugged. Designers were still not sure what the lunar surface would present. All previous suits had been fed with oxygen and power from an external source. The moon suit had to be self-contained, and the backpack supplying life support presented problems. The backpack's dimensions and weight were determined by extensive testing, and designers of the life support, battery and communication systems worked within strict parameters. After the Apollo 1 tragedy, flammable components had been removed, and an outer layer of beta cloth, of woven silica fiber coated with Teflon, was added. Many different ways of simulating the moon's 1/6 gravity were trialed. Finally, the A7L suit emerged. Beneath the outer layer, a tight-fitting suit with elbow, wrist, and knee joints of a bellows-like structure that maintained equal volume when bent, allowed freedom of movement absent in previous suits. Beneath the pressure suit, a light open-weave layer was networked with fine tubes circulating cooling water. This carried away excess body heat that earlier air-cooled suits had not coped with. The pressure suit and the outer protective layer were joined together, with the inner cooling garment remaining separate. On Earth, the whole suit weighed 35 kilograms, with the backpack a further 60 kilograms. It was the A7L that went to the moon with the first 3 successful Apollo lunar missions, and it performed flawlessly. It continued to evolve as subsequent missions became more demanding. The moon suit was robust, and Apollo astronauts had complete confidence in it. No lunar mission ever had a problem with the spacesuit.
have maintenance and stuff.
With the arrival of the space shuttle, NASA was expecting to do serious work in orbit, and it needed a new spacesuit. The Extravehicular Mobility Unit, or EMU, is a direct descendant of the Apollo A7L. Its main difference is the rigid upper torso. Because they are used in a weightless environment, the new suits could be heavier than the Apollo suit, which operated in lunar gravity. The EMU is not custom-tailored for each user. Components are made in a range of sizes and are interchangeable. Parts are intended to have a useful life of around 15 years. With the shuttle, NASA envisioned servicing satellites in low Earth orbit, but first it had to learn how to do simple tasks. New technologies were combined with the spacesuit. In 1984, astronaut Bruce McCandless, using the Manned Maneuvering Unit, flew independently beside the Space Shuttle Challenger. After 4 hours, he returned safely. The MMU was used for satellite recovery on 2 subsequent occasions, with mixed results. After the Challenger disaster, NASA reviewed all aspects of safety, and the MMU was retired as too risky. A simpler technique emerged. With foot restraints on the shuttle's robotic arm, astronauts could be moved accurately to a site and have a stable work platform. In 1990, the Hubble Space Telescope was launched. Unlike other satellites, Hubble was designed to be visited by the Space Shuttle for regular maintenance and upgrades. Over a 16-year span, there were 5 servicing missions to the telescope, the first being to fix an error in its manufacture.
Is a game-ending activity.
Each servicing mission called for long and complex spacewalks. The EVAs were all thoroughly rehearsed in NASA's Neutral Buoyancy Laboratory. The astronauts are weighted so that they neither rise nor sink, and all the large components that they handle are similarly neutral. Astronauts still have the perception of up and down in neutral buoyancy, unlike in weightlessness. In 1998, work commenced on the International Space Station, a collaboration between the US, Russia, Europe, Japan, and Canada. This was the type of project for which the Space Shuttle had been designed, and the expertise that NASA's astronaut corps had gained was to be put to use for on-orbit construction. As the space station grew, the EMU spacesuit was refined. Increased battery capacity was added so that small heaters in the gloves could keep astronauts' fingers warm during passages through the Earth's shadow. A new safety system was added to the EMU suits. Called SAFER, the Simplified Maneuvering System is designed for emergencies in the rare event that a spacewalker becomes untethered from the space station. It was first tested in 1994, but it has never been used for an actual emergency. With the completion of the ISS in 2011, the Space Shuttle was retired. This meant sole access to the orbiting laboratory was via the Russian Soyuz spacecraft. Cosmonauts and astronauts wear the Russian Sokol flight suit during trips to and from orbit. For maintenance and repair sorties outside the ISS, crew will wear either the EMU or the Russian Orlan spacesuit. Many of the Europeans on board have training in the use of both. The Orlan spacesuit is very practical, designed to be serviced on the space station. It has a rigid torso, with the helmet and visor joined to the suit, and access is via a rear hatch. Cosmonauts wear a water-cooled undergarment similar to the American suit. Unlike the American suit, the Orlan can be put on in just 5 minutes. In the MKS, the latest version of the Orlan, a cosmonaut can safely remain outside for 7 hours. And finally, NASA is working on a new generation suit to meet its future needs. Called the PXS for Prototype Exploration Suit, it also features a rear entry hatch. The PXS has a more advanced life support system and is lighter. A different version, called the Z2, is being developed for use on the surface of Mars. It allows a greater range of movement, and its life support system will take less time to recharge, although neither suit has yet been used in conjunction with its life support backpack. Some of our solar system's planets have been visited by scientific probes less frequently than others. The outer gas giants, Uranus and Neptune, are so distant they're hard to reach. Uranus is 20 times further from the Sun than Earth, while Neptune is 30 times further. Both have only been seen at close range by NASA's Voyager 2 spacecraft. Mercury is so close to the Sun that any probe sent in its direction must take a circuitous path to offset the Sun's immense gravitational influence. The Mariner 10 probe flew past Mercury in 1973, and the Messenger probe went into orbit around Mercury in 2011. Venus presents different problems. Though it's our closest planetary neighbor and easier for spacecraft to reach, dense cloud hides its features and its surface has hellish conditions. The Russian Venera craft have landed, but in the hostile environment, they could only survive for minutes. Roughly twice every century, the planet Venus passes between the Earth and the Sun. Called the Transit of Venus, it was closely observed in 1769. Astronomers realized that careful timing of Venus's passage across the face of the Sun would allow them to calculate the distance to the Sun, which in turn would unlock far more accurate methods of navigation. In 1961, the Soviet Union launched Venera 1, the first Venus probe. It passed Venus as intended, but mission control had lost contact with it. The following year, NASA launched Mariner 1 to Venus.
We're not on trajectory.
A coding error led to control problems with the launcher.
Destruct command.
It was destroyed minutes after liftoff.
Battery blew up.
Because convenient launch opportunities only occur in 18-month cycles, NASA had a second probe ready to launch. Mariner 2 was essentially a Ranger spacecraft designed to go to the Moon. These were the early days of the space race, and the United States was desperate to catch up with the Soviet Union. Lead times were short, and the Jet Propulsion Laboratory did not have time to complete its original design. In August 1962, Mariner 2 was launched. The Ranger spacecraft launched toward the Moon had all failed. Mariner 2, on its way to Venus, was functioning, but its transmissions were weak, and due to a launch anomaly, it was off course. After a week, instructions for a complex course correction were transmitted to the spacecraft. About an hour later, Mariner executed the maneuver, which involved a roll turn, followed by a pitch turn, and finally a main engine burn. It worked well, but several days later the craft lost lock on the Sun and the Earth, its two attitude reference points. It corrected itself before ground control could diagnose the problem. Next, the signal strength increased to its normal level, but a short in a solar panel left it low on power. At this time, although both America and the Soviet Union had been sending probes toward the planets, nothing had succeeded. Mariner 2 lost several telemetry sensors and it began to overheat. It continued limping toward Venus, but some of the spacecraft's problems were solving themselves. Mariner 2 was now close enough to the Sun that it could function effectively on just one solar panel. It passed slightly less than 35,000 kilometers above Venus's cloud tops. It could detect no planetary magnetic field, and it recorded temperatures across the planet approaching 500 degrees Kelvin. Clearly, landing on the surface would present problems. But America wanted to focus on their first real success in space, finally doing something that the Soviets had not. Mariner 2 was the first successful interplanetary probe, and in California, the home of JPL, they celebrated. The next major advances in the exploration of Venus were made by the Soviet Union. The objective of the Venera series was to land on the surface of Venus. Designers understood that not only were the surface temperatures hot enough to melt lead, but that the atmospheric pressure was many times that of Earth. The landers they built looked more like diving bells than spacecraft. In June 1967, Venera 4 was launched. The vehicle consisted of a carrier craft with instruments used during the cruise phase to Venus and a spherical landing module that could communicate independently. After entry into the atmosphere, Venera 4's parachute opened. It sent back data for 93 minutes, but stopped 28 kilometers above the surface. Yet its electronics hadn't been overwhelmed by the heat. It had simply run out of power. Extrapolations from its final measurements showed a surface temperature of 500 degrees Celsius and a pressure of 75 atmospheres, far higher than anyone expected. The Venera program strengthened its landers and fitted smaller parachutes to reduce descent time. Launched in January 1969, Venera 5 and 6 learned more about the chemical makeup of the atmosphere, but neither remained functioning at the surface. The Venera series continued, refining the technology and making incremental improvements to mission duration, adding to the knowledge about Venus. In 1975, Venera 9 was launched. It was a new design, consisting of an orbiter-lander combination, with the orbiter able to act as a relay station for signals transmitted from the surface. 4 months after launch, the orbiter and the lander, encased in a spherical shell, separated. It entered the atmosphere 2 days later, while the mother craft became the first probe to go into orbit around Venus, photographing parts of the surface in ultraviolet. The new lander had a ring shield that could replace a parachute during the latter stages of the descent through the dense atmosphere. Venera 9 transmitted the first black and white pictures from the surface, though a design fault meant a second camera could not eject its lens cap. 3 days later, and 2,000 kilometers away, a twin craft, Venera 10, landed. It took pictures too, but the same design fault left a lens cap stuck in place. Both landers had been pre-cooled while still in space, and circulating cooling fluid kept the craft operating on the blistering surface for more than an hour. In 1983, 2 more Venera craft arrived at Venus. Equipped with synthetic aperture radar, they made the first serious attempt to map the surface beneath the cloud layer. Over 8 months, they mapped from the North Pole down to 30 degrees north.
T-minus 10, 9, 8, 7, 6.
NASA had taken a minor role in the early exploration of Venus. But in 1989, the space shuttle Atlantis lifted off carrying the Magellan probe. Magellan was bound for Venus. Like the Venera craft before it, Magellan would use radar to map the surface of the planet. It was the first interplanetary spacecraft launched from the space shuttle. Following a cruise of 15 months, Magellan arrived at Venus and entered an elliptical orbit. To keep costs down, the probe had been built from an agglomeration of spare parts left over from previous NASA missions. After some software problems, it began mapping. The images it relayed remain the highest resolution pictures we have of the surface of Venus. Pictures of low volcanic blisters emerged, and lava channels were evidence of an extremely active surface. The thick atmosphere has prevented all but the largest meteors reaching Venusian ground, and few impact craters were visible. Yet evidence of plate tectonics that sculpts the Earth's surface was not obvious. After mapping Venus, Magellan changed its orbit and plotted the planet's gravitational anomalies. On Venus, localized changes in gravity correspond to surface features. On Earth, this is not the case. A new naked picture of Venus emerged. The surface appears to have been completely remade around 500 million years ago. Yet while volcanoes and lava channels are common features on Venus, Magellan could not find evidence that volcanic activity still happens on the planet. In 2006, the European Space Agency's Venus Express went into orbit around Venus. Its focus was the long-term analysis of the planet's atmosphere. During its 8-year mission, it registered a sharp rise in the atmosphere's sulfur dioxide. This could be due to changes in wind patterns, but it could also be a sign of volcanic activity. Researchers also saw increases in infrared radiation coming from 3 different volcanic locations. More circumstantial evidence of current volcanic activity. Finally, the infrared team saw short-term temperature changes that fluctuated over just a few days. It appears that volcanoes may still be active on Venus. The mission ended in 2015 with a series of swoops into the upper atmosphere that verified unexpected ripples in the mesosphere. Very little in the way of Venus exploration has happened since Venus Express. Though elaborate plans exist for future missions to Venus, nothing at this stage has been funded. Yet many missions still pass close to Venus to use its gravitation to alter their flight paths. In 1974, Mariner 10 was the first spacecraft ever to use the gravitational slingshot effect on its way to Mercury. Italian mathematician Giuseppe Colombo devised the maneuver as a way to save fuel and to fly past Mercury not once but several times. The technique is now commonplace. 10 days after launch, Mariner 10 executed instructions for a routine course correction. This appeared to go well, but after the burn, when the craft attempted to reorient itself, there was a problem. Mariner 10 knew where it was pointing because its tracking sensor could lock onto the star Canopus, but a flake of paint that had come from the spacecraft was confusing the system. An automated backup procedure found Canopus again, but flaking paint was an issue for the rest of the mission. To reach Mercury, a spacecraft must approach the Sun, and its immense gravity presents a problem. Voyages to outer planets are constantly slowed by solar gravity, but with the inner planets, a spacecraft constantly accelerates. Mariner 10 used Venus's gravity to reduce its speed, and it approached Mercury at an acute angle. Mariner 10 did not have enough fuel to go into orbit around Mercury, but its sun-centered path allowed the probe to make 3 close passes. Its first pass revealed a moon-like planet with a heavily cratered surface. Though Mercury is the smallest planet, it's the most dense. It has a large, iron-rich core. Prominent escarpments were seen. Here, Discovery Scarp cuts through 2 craters. It falls 3 kilometers. It's thought that these cliffs are the result of cooling and shrinking of the core. Mariner 10 continued to suffer technical problems. Its tape recorder kept sticking. There were restrictions in the rates of data transmission, and limited attitude control meant flight engineers were using solar pressure on the high-gain antenna and solar panels to compensate. Yet the mission continued. Mariner 10 could only map about 45% of Mercury's surface, as the same hemisphere faced the Sun during each of its passes. Mariner 10 discovered a very thin atmosphere, primarily of helium. Several months after its third and final pass of Mercury, it ran out of fuel. It still orbits the Sun.
Main engine start, 2, 1, and 0.
It was more than 30 years before the next mission to Mercury. In 2004, Messenger was launched. It was designed to go into orbit around Mercury, which presented a number of design constraints. It featured a large woven ceramic sun shield, but it did not have a dish antenna. It would rely on a phased array that could be electronically pointed. After a year in space, Messenger was back at Earth, using its gravitation to modify its orbit. Even though it was not a large spacecraft, it had a powerful engine for course corrections and orbit insertion. It continued on to pass Venus twice to lose speed as it drew closer to the Sun. 3.5 years after launch, Messenger approached Mercury, but this was not the end of its journey. The probe made 2 more passes of Mercury before finally going into orbit after almost 7 years in space. Mission engineers had the extra problem of always requiring the probe's sun shield to be pointed toward the Sun. Because it was in orbit, Messenger was able to complete the mapping started by Mariner 10. The planet's dominant feature is the Caloris Basin. It's an ancient crater more than 1,500 kilometers across. Mariner 10 saw some of the area, but the rest had been in darkness. This map of the southern polar region uses color to represent illumination. Because Mercury's axis is not tilted, sunlight cannot penetrate deep craters near the poles. It was in these areas that Messenger discovered substantial amounts of water ice. Messenger received several mission extensions, but in 2015 it crashed into Mercury after running out of fuel. A new mission is already on its way to Mercury, Bepi Colombo, named after the designer of Mariner 10's trajectory. It's a joint effort between JAXA, the Japanese Space Agency, and the European Space Agency. It will take 7 years to reach Mercury. The Voyager 2 spacecraft is the only probe to have made close approaches to the two outer ice giants, Uranus and Neptune. Launched in 1977 with its twin Voyager 1, it was able to take advantage of a rare alignment of the four outer planets, enabling it to make close observations of each one. In 1986, Voyager approached Uranus. In the distant past, it must have been hit by another massive body that knocked its axis sideways. Uranus has an east and a west pole, and for half its orbit, one side sees continual sun, while the other remains in darkness. It has rings which follow its north-south equator. Voyager 2 discovered 11 new moons and a misaligned magnetic field. Images that the Voyager captured showed Uranus as a bland, featureless planet. But this was because of its particular season. With images from the Hubble Space Telescope, we now know that at certain times clouds and planetary weather appear in the atmosphere. Uranus's largest moon, Miranda, was observed in detail for the first time. So chaotic is its surface that researchers thought that it must have been blown apart by some cosmic impact, with the fragments reforming. Now it's thought that tectonic forces, initiated by the gravitation of Uranus, are responsible for the moon's jumbled appearance. As Voyager 2 left Uranus, backlighting from the sun revealed two new rings encircling the planet. The spacecraft was now heading toward Neptune, the solar system's last planet. In the 3 years it would take to get there, ground engineers began preparing for unique challenges. Neptune is 30 times further from the Sun than the Earth, and the light intensity is 1,000th what it is here. For photography, time exposures would be necessary, yet Voyager 2 was traveling so fast that images would smear without special preparation. Engineers calculated just how much the craft would have to swivel while exposures were made to compensate for the probe's movement. In June 1989, Voyager 2 began returning distant images of Neptune. Across the world, people had realized that the data sent back to Earth by this spacecraft was transforming our understanding of the solar system. This was before the internet age. Researchers at the Jet Propulsion Laboratory clustered around TV sets to watch as data and images came in line by line. Neptune is a more conventional planet than Uranus. Its axial tilt is 30 degrees, and it revolves in the same direction as Earth. While Neptune is slightly heavier than its fellow ice giant Uranus, it has a slightly smaller diameter. And, though it is further from the Sun than its neighbor, Neptune emits more heat than Uranus. The planet has an internal heat source that drives more dynamic weather patterns. Voyager 2 measured wind speeds at Neptune in excess of 2,000 kilometers per hour, the fastest in the solar system. There were cirrus clouds in the atmosphere, and the probe recorded pictures of a great dark spot, similar to Jupiter's Great Red Spot. It was an anticyclone in the southern hemisphere, as large as the Earth. In 1994, when Hubble tried to find the same feature, it had disappeared, but a new dark spot was forming in the northern hemisphere. Voyager 2's last observations within the solar system were of Neptune's largest moon, Triton. Unlike all other moons in the solar system, Triton has a retrograde orbit, indicating that it was not formed at the same time as the planet, but that it had been captured. As Voyager 2 moved beyond the planets, its cameras were switched off to save power. Both Voyagers continue away from the solar system, measuring the influence of the solar wind. This remains the only mission to the ice giants. On January the 19th, 2006, an Atlas V was launched. It was a very powerful rocket with an unusually small payload. New Horizons left Earth orbit faster than any other probe. It was headed for the Kuiper belt at the outer edge of the solar system, in particular Pluto. In a little more than a year, New Horizons reached Jupiter, where it received a gravitational assist that cut 3 years from its flight time to Pluto. After it passed Jupiter, the spacecraft went into hibernation, simply sending an all's well transmission once a week. It took New Horizons more than 9 years to reach Pluto. Since it had departed, Pluto had lost its status as a planet. With the discovery of more objects of similar size in the Kuiper belt, it was decided that to be a planet, a body had to clear its orbit. Pluto's features surprised everyone. Here was a living planet shaped by tectonic forces, but instead of rock, the mountains were made of ice and frozen methane. And Pluto has a thin atmosphere, mainly of nitrogen. The probe continued on over Charon, Pluto's largest moon. Its icy surface has deep canyons, and some evidence suggests that it has ice volcanoes. Charon is about half the size of Pluto, and the two orbit each other. From Pluto, Charon would appear motionless in the sky. As the New Horizons probe sped away from Pluto into deep space, it began the slow process of transmitting its recorded data back to the Earth. At these distances, it takes signals 4.5 hours to reach Earth, with data coming in at 1 kilobit per second. It took 469 days for all the Pluto information to be received back on Earth. Early in 2019, New Horizons passed trans-Neptunian object Ultima Thule, and with a mission extension, it continues exploring the outer reaches of the solar system.